we need to appreciate that surface grinding or any grinding is very important in the machining trade. So surface grinding, it's only one of the types of grinding that we deal with in machining. Surface grinding is a type of grinding that allows us great accuracy. So we can hold really, really tight tolerances. So let's say, for instance, you're looking at a print and the print calls out a surface finish of a certain surface finish. Let's say a 32 surface finish, which we'll talk about later. But it's also it requires that we have control the thickness of a part to 1/10 of 1/1000th of an inch, so 0.0001 inches. So we can, with a surface grinder, we can cut surfaces that accurate. We can create sizes that accurate, while at the same time we can create a surface finish that is mirror-like. So how does surface grinding work? Was kind of the premise of it. So it's a process where your workpiece is brought into contact with a revolving grinding wheel. So we'll talk about that for a little bit now. So there's various ways to grind metal, guys. So there's pedestal grinders. So what's a pedestal grinder? You'll have seen those in a shop. You're going to see them in your shop. Pedestal grinder, it is exactly that. It's two grinding wheels sitting on a pedestal, right? And so you turn it on, and we would use that pedestal grinder for like non-precision type grinding. We can grind, we can sharpen a drill, sharpen a cutting tool, create a shape for a cutting tool. We can also grind off high spots on welds, remove burrs, right? Or put rough chamfers on parts. That's primarily what a pedestal grinder is for. But for precision grinding, we have some other options now, right? So now pedestal grinders are not for precision. It's just to remove material. But we have, for precision grinding, we have surface grinder, which is what we're going to talk about today. We have the cylindrical grinder, and we have the centerless grinder. Now, regardless of the grinder that we choose to use, centerless, cylindrical, or surface grinder, the process is the same, and there's some general rules that apply to all three. What we're going to focus on is the surface grinder. So make note here, guys, there are 4 types of surface grinders that you need to be aware of, okay? 4 types. Number 1, there is the horizontal spindle grinder, okay? The horizontal spindle grinder with a reciprocating table. So you've got the horizontal spindle grinder with reciprocating table. Okay, that means the table reciprocates, moves back and forth. You have the horizontal spindle grinder with a rotary table. Okay, horizontal spindle grinder with a rotary table. And then you have the same 2 grinders, but in the vertical style. So you have the vertical spindle grinder with the reciprocating table, and the vertical spindle grinder with a rotary table. So let's talk about the horizontal spindle grinder here for a second, guys. So the wheel head, which you see here on the left-hand side. So this here is the wheel head on this dual grinder, and this here is a wheel head on another type of surface grinder, but it's the same thing. The wheel head, it houses the spindle, and it can be adjusted in the Z-axis. So you can accurately adjust this wheel head to 0.0001 inches. Very accurate, okay? You can adjust it in the Z-axis up and down to 4 decimal places of an inch. Okay, so when you go to manufacture your 1, 2, 3 blocks at the school, Remember we talked about leaving a certain amount of material on the 1-inch side, the 2-inch side, and the 3-inch side. Well, if we are leaving material on, you might have been thinking, well, if I leave material on, how am I going to get it off, right? Well, this is how you're going to get it off. So it's important that we leave enough material. We don't leave too much, but we want to leave enough material so that we can grind the part into size accurate to 1/10 of a thou. So the spindle, and by extension the grinding wheel, since it's mounted on the spindle, they run at a consistent spindle speed. Okay, so we're talking about manual surface grinders. Okay, so there are some CNC surface grinders, lots of them. I shouldn't say some, there's lots, where you have a little bit more control over things, so you can control your spindle speed. But for the most part, manual surface grinders, you turn on the spindle and it runs at a very specific speed. It runs at that speed all the time, one speed, okay? Now the table where the work is mounted, in most cases, can be moved manually as well as automatically. So we're talking about the horizontal spindle grinder with the reciprocating table, right? So that is that this table will move in the x-axis, at least in the x-axis, automatically. And we would set that auto feed somewhere on this machine. There will be table feed control levers. We'll set the table feed right there, and then we will set the table dogs here. So these dogs, basically what they do is they tell the machine when it's traveling to the left, it stops on a dog and reverses, stops on a dog and reverses. So that's how we get that reciprocating motion. Okay, so but you can also disengage the automatic feed, that auto reciprocation, and you can manually, see here, you have a cross feed hand wheel and a table traverse. So this is your X hand wheel, X manual hand wheel. This is your Y manual hand wheel. So you can actually move the table in X and you can move the table in Y to manually grind the surface of this part. The advantage, of course, to the auto feed on the X and Y is for greater control of that surface finish. So on prints, we won't just have dimensions that we have to cut, like plus or minus 1/10. Let's say, for instance, we got to cut your 1, 2, 3 block is 1 inch. Maybe your instructor says, I want you to cut it accurate to 0.0002 inches, 2/10 of a thousandth of an inch. Well, you can cut that height. You can absolutely cut your block to 1 inch plus or minus 0.0002 inches, no problem. But with that reciprocating motion, that auto feed motion, you not only can control your height fine, but you can also control your surface finish better. And that surface finish is a different call out. That's the amount of waviness at a microscopic level that you cut that surface to, right? So you have control over that as well, which is just absolutely amazing. The calculated speed of the spindle and the feed of the work, they're both required to achieve this optimum cutting performance. So in other words, feed and speed work together to allow us to create the surface finish we want. But we have some limitations. Now, mind you, the speed and feed combinations, they have less of an impact on the surface finish when we grind compared to milling or turning, because the spindle speed turns at a constant motion. Let's say it's 3,500 RPM. We'll always turn at that. So if we know that we have to deal with a 3,500 RPM always on the material we're cutting, then we can adjust our feed rate to compensate for the spindle speed, which we can't change. One thing that you're going to learn in this course is that feed and speed, they are relative to one another. So when I explain to you how to solve RPM so you get the best rotations per minute for the best cutting action for the material you're cutting and the tool you're using, you also need to figure out how fast you move that tool into the material. So not only how fast the spindle goes, but how fast the material moves in and out, or the tool moves back and forth on that material, has an effect. And the RPM and the feed rate, they're relative to one another. You need to know the RPM to figure out the feed rate. So if your RPM is set, like on a surface grinder, to 3,500 RPM and you can't change it, you can at least use that information to solve the best feed rate to accomplish the surface finish that you want to get. Okay. All right. Surface grinding, all it is a technical term referring to the production of flat, contoured, or irregular surfaces on a piece of work, which are passed against a revolving grinding wheel. So if you look in this picture here, here's an example of the grinding wheel on the arbor, cutting a piece of material sitting on top of the table here. Okay, so as the workpiece, okay, so this here is our workpiece. This looks like this bar right here is our workpiece. As that workpiece is brought into contact with this cutting wheel, every one of these small abrasives is brought into contact with this material. So these are the abrasives, okay, on the cutting wheel. That rough surface, if you look at it at a microscopic level, they're just made up of several little abrasives. And those abrasives, they're not just on the periphery of the wheel. The whole wheel is made up of these abrasives. But the abrasives that come into contact with the material actually cut the material. They actually remove a chip of material, right? They're cutting this little bit of material. And notice these are all irregularly shaped abrasives. They're not like a precision cut abrasive embedded in a bond. It's just a granular, a particular grain size of abrasive formed into this wheel. And those abrasives, when they come into contact with that material at that RPM, they remove a small piece of material off your part. So we'll talk about that for just a couple of minutes here. Okay, workpiece, magnetic table. The magnetic table is what holds the workpiece down. There's you're gonna have to get your hands on the surface grinder to really respect what this machine can do and what kind of damage it can do if we're not proficient with our handling of the machine. Imagine you have a grinding wheel turning at 3,500 RPM. Go sit in your car, have your wife rev it up to 3,500 RPM, and then stick your head in there, right? This is what we're talking about. That wheel is going to come into contact with your workpiece. Now, I'm going to tell you right now, this is a large workpiece. Typically, you're going to be working in your training anyway. Everything's small. So the smaller the workpiece, guys, the smaller the contact down here on the table. So the less contact, the less secure, right? And one of the things that are so important to us as machinists is rigidity. Rigidity. You need to think rigidity, right? So if my workpiece is smaller, I have to make sure it is in contact with as many magnetic strips on this plate as possible, because I'm bringing this 3,500 RPM wheel down and I'm going to touch it. What do you think is going to happen to that workpiece if it's not mounted properly, right? It's going to go, right? So we need to consider that. This magnetic table, guys, neglecting to turn that table on is disastrous. No word of a lie, I have seen a grown man drop to his knees and cry when he forgot to put his magnet on. Now, part of the reason he cried was the amount of noise and the distance that the 72 pieces on this table went when that wheel came down and tried to cut, and none of those pieces were magnetized. So it would be like taking a baseball bat, right? to a bunch of glass vases, nothing holding them down. Just so it shot these parts 50 feet across the shop right into a concrete wall. Not to mention the tens of thousands of dollars in loss in revenue. So guys, if you're not sure, ask which direction is the magnet on, right? And as you can see in this diagram here, it's not easy to tell. I mean, this is just an artist's rendition of this, right? It's not easy to tell. In some cases, the handle here, right? This handle is in the forward, the forward position when the magnet's on. But I've had magnets that have been refurbished, and when the millwright put it back together, he put the handle on backwards. So the on position was this way. So there's easy ways to tell, right? You can put a part down on top of the magnet as long as it's magnetic, right? And engage the magnet. If it doesn't move, your magnet's on. If it moves, well, your magnet's not on. Let's go back to kindergarten, right? But this is the key, okay? Due diligence. When you put your part down on that table, first of all, that table has got to be clean, dust-free. If you can cut as accurately to 1/10 of 1/1000th of an inch, then can you also not appreciate that any chip, burr, dust, dirt, oil can throw your part height out or throw it out of square? Okay, that magnetic chuck vise has got to be clean. Your part has to be burr-free. No chips, no burrs, right? So it can sit flat, and when you engage that magnet, the entire surface of your part is magnetized on that magnetic chuck, okay? I think I said that with enough stress in my voice that it makes sense, okay? So due diligence, right? So once you've magnetized your work, check it, grab it, pull, push, right? Make sure that it is secure. I will say to you this one thing that may kind of put your mind at ease a little bit. Notice the rotation of the wheel. So on this side where it says magnetic table, this is where you stand, right? So the table, this is your x-axis. X is back and forth this way. This is your y-axis right here. You're standing right here. And this table is moving back and forth, back and forth, back and forth. If this piece, for any reason, comes loose, which direction is it going to go? Right? It's going to go this direction, this direction. It's going to go to your left, right? So my table is moving left and right like this. The material is going to go that way to my left. So guess where you never stand, right? You never stand on this end. People have died, guys, standing on this end of a surface grinder while it's running. You'll notice at the shop that this end is a wall for that very reason, right? So guys, the work will only launch in one direction. That's not to say that the wheel, when it launches apart, won't explode and go in every direction. Okay, so again, it's not to scare you, but you need to really understand 3,500 RPM, auto travel, back and forth, in and out. You don't have a chance of stopping that. Okay, so due diligence. Clean table. Make sure your material is covering as many magnetic strips as possible. That may mean that you may need to rotate your part on an angle to catch one more strip. Okay, and make sure your part is burr-free and chip-free. Clean, flat surface. Make sure, and then double check, and then triple check, because you don't want to launch a part. And even if you don't launch the part, if you have a 0.0002 inch, 0.2 of an inch burr on one side that you can barely even feel, that can put a taper on that part 1 thou or more, right? So I think I've beaten this horse to death. Okay. Once we have cleaned our table, we've put our part on the table, and we're ready to surface grind it. We're ready to grind a nice finish on that part. One of the things we absolutely have to do is we have to dress the wheel. Now, there's two opportunities here. One opportunity is to get your diamond dresser, dress the wheel, then clean your table, then mount your workpiece, and then cut it. The other option is that you mount your workpiece and your diamond cutter as long as your diamond cutter will not come into contact with that wheel in the cutting action. Okay, so you'll never guess which way we prefer at the college, right? The first way. So the first way is that you dress your wheel before you mount your part. So dressing the wheel, basically what we're doing, remember in that first slide here, I showed you guys the grains of the wheel, right? So those grains of the wheel, what happens is they, as those little tiny abrasives are cutting material, they'll break off, right? And they'll expose new abrasives. But they don't all break off at the same time, right? Because remember, they're just random shapes. So some will break off earlier than others. So you can imagine that over a certain amount of time, the face, right? So this, oh my goodness, where's my mouse? There it is. So the face of this wheel is going to change in size and release abrasives during the cutting process, and not in any type of symmetrical way. They'll just come off as the bond releases them. So before we grind a part, we want to dress the wheel. And dressing the wheel means basically making the bottom of this wheel, the flat part of this wheel, perpendicular to the side of the wheel, right? So essentially, I don't know if I can draw it in front of, oh, I don't have the right camera. Here, let me just switch cameras for a second here. So if we just go here, okay. So this is the side, looking at the side of the wheel, right? And this is looking at the wheel from this side here, okay? We want this face, which is here, to be perpendicular to this face, right? So this is the face we dress right here. We want it to be perpendicular to this face. So this and this must be perpendicular if we want to grind a flat surface on our, if we want to dressing the wheel makes that surface perpendicular to the to this part of the grinding wheel right here. Okay, so what we do is we take this diamond dresser. Notice it's sitting on a piece of paper because this magnetic table requires care, right? So since we're just dressing this is not something that we would do with any of our parts. We just do this with the diamond dresser, and you don't have to. Okay, but it's good practice. So you put your diamond dresser down on a piece of clean paper, engage the magnet, turn the spindle on, and then notice from the side view here, the diamond dresser, the diamond is actually set up on a 10-degree angle. So you can buy them at 10 degrees or 15 degrees. The reason is we don't want that dresser perfectly vertical, because remember we talked about a tangent point, right? So this wheel coming into contact with the point of the surface in a straight line, you only have to be slightly off center for that wheel to hammer straight down into that diamond. So by tilting that diamond on a slight angle, you're not coming straight down on the point. You're just kind of coming down on the side of that point. So there's a little bit more forgiveness if you don't have the diamond dresser set up in exactly the right place. So notice the location. This line right here, this line is the center of the wheel. It's the center of the spindle. The diamond dresser is in front of the center line. It is not straight on the center line. That makes as much sense as having the diamond vertical. The diamond is set on a 10-degree angle, and it's set ahead of the center line of the wheel. By how much? Well, that's up for debate. I like to set it up minimal, 50 thou, 0.05 by eye. This looks like it's probably a bit further, maybe 150 thou. But the idea here, guys, is to just not be on the center line, be in front of the center line. For the love of God, don't be behind the center line, because as the wheel comes around and the low spot, this is the lowest part of the wheel right here. You do not want this part of the wheel or anything behind it trying to coming into contact with your diamond. You want it to come in contact with the diamond before it reaches the center line, because then you're actually removing material, right? You're not grinding away the back of the diamond. You're removing material on the point of the diamond. So the diamond is on a 10-degree angle. It's set ahead of the center line. You turn the spindle on, and then as you see here in this picture, you would move the y-axis back and forth like this to dress that wheel. So how much material do I take off? How low is this wheel here? Guys, minimal, right? So what you're going to do is you're going to have your instructor. He's going to walk you through this the first time. Wheels running, dressers on, and you're going to start moving the table in and out, in and out. And then you're going to go down a couple tenths, in and out, couple tenths, in and out, couple tenths, in and out. And then you'll hear, tss, 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 right? Barely kissing it. Now you know, basically that's your zero, right? You're just touching the wheel. Then I would probably say 5 tenths at a time. I wouldn't even take 0.001 off. I'd 0.005 maximum for me. Okay. You can be more aggressive. In some cases, you may have to be more aggressive to get, like, especially if you've loaded up that wheel. Maybe you tried to cut a material that wheel is not designed to cut. Maybe you tried to cut aluminum with an aluminum oxide wheel. Well, now you're going to load up the teeth. So you have to maybe take a little bit more of an aggressive cut to get that garbage out from between the abrasive cutting edges. But, 5 tenths at a time, guys, 0.0005, a maximum for me. I hope I didn't say 5 tenths, okay? 0.0005. I'll go as much as 1 thou, 0.001. I'll go as much as 1 thou, depending on the wheel that I'm trying to dress. Once you've dressed it, you can look down the side of that wheel once you've dressed it, right? So once you've dressed this bottom, now you can look down, look at the back of that wheel, and you'll see that this whole surface of the wheel, because it spins, will all look nice and crisp, right? So if it's, let's say it's a white colored grinding wheel, the whole wheel will look white. You won't have any gray spots or black spots. If it's a pink wheel, same thing. You'll have a consistent pink color. You won't have any wear spots. If you see any discoloration at all, then you don't want to be afraid of dressing it some more. But guys, dress it till it's done. Because once you take that diamond dresser off, if you realize, oh crap, I missed a spot, you can't just put it back on. You got to clean the table again. You got to clean the bottom of your dresser, because everything has to be perfect, right, before you can dress it a second time. So we've talked about the surface grinder. We need to understand more about the grinding wheel itself. There's a few things we need to know. So number one, we need to know about the abrasive. Okay, what is the abrasive? So basically, the abrasive is the part of the grinding wheel that does the cutting, right? The abrasive is the part of the grinding wheel that does the cutting. We saw that in that PowerPoint presentation. They're just they'll all be the same grain size, let's say. Okay, so they'll have a certain size, but they won't all be the same shape. Okay, so the abrasive is the part that does the cutting. There's two types of abrasives that you need to be familiar with. Okay, so number one is the aluminum oxide abrasive. Okay, so aluminum oxide, they make up about 75% of all grinding wheel abrasives. Okay, so that is the most common type of abrasive, is the aluminum oxide. So what do we use it for? So we use it for all non-ferrous metals except for cast iron. Okay, so all non-ferrous metals except for cast iron. So these will all be high tensile strength materials. Okay. So aluminum oxide is manufactured with different grades of purity. So the most common is 94.5% purity. Okay, that is the most common aluminum oxide purity is 94.5. The reason you'll know if the aluminum oxide wheel you've chosen is this common 94.5% is it'll be grayish in color. Okay, so the colors of the wheels, they're not like slightly different from one another. They're vastly different. So you're a grayish colored aluminum oxide wheel is 94.5% pure. So this is what you're going to see for basically what you're going to grind. Your 1, 2, 3 blocks. That's going to be this, right? It's going to be an aluminum oxide, 94.5% purity. Now, you can get 97.5% pure aluminum oxide abrasives in your grinding wheel. But typically you're going to see this abrasive, this aluminum oxide purity level is going to be more in grinding wheels for like cylindrical grinders, centerless grinders. Now, these are a harder abrasive. The more pure, the harder, but also the more brittle. Okay, so that's worth noting. So the harder it gets, and that's a pretty common rule in machining when it comes to metallurgy. The harder a material gets, the more brittle it becomes. Okay. So the other abrasive. So did I put that? So let's put that aluminum oxide, right? Aluminum oxide. 94%, 94.5% pure, most common. So that's the one type of abrasive. The other type of abrasive is silicon carbide. Okay, so silicon carbide is best suited for grinding materials that have a low tensile strength. So like your aluminum, your brass, your bronze. Okay, so that's what we would choose the silicon carbide for. It's also used for cast iron. So remember we said that this first sorry, once again, too many screens and I've lost my mouse. There we go. Okay, so remember that we said that aluminum oxide is used for high tensile strength and all ferrous metals, right? While silicon carbide is going to be for low tensile strength and non-ferrous metals, right? Non-magnetic metals. So we will also use silicon carbide for materials like if we needed to grind like a cemented carbide insert, we could use silicon carbide for this. Because remember that carbide is non-magnetic, right? So that will help us in carbide is non-ferrous, right? It's non-magnetic. So typically the colors of the silicon carbide, they go from a green to a black. So you're not going to get a gray, right? And that's our aluminum oxide. It's going to be like a green to a black. The green wheels, they're used for cemented carbide. So you might have seen these. You might have actually been in a shop where you see a pedestal grinder and one of the wheels is green. I mean, it is noticeably green. You would never want to take a piece of ferrous metal, like a high iron content metal, and try and grind it. You'll just load that wheel right up. It'd be just like mashed potatoes. That green wheel is for carbide, to sharpen carbide tools. Way cheaper than going to buy another carbide tool. And then the black wheels are for grinding like the cast iron and other soft non-ferrous metals like brass and bronze and aluminum. Okay. Now it is interesting, just if you didn't think of it, remember that on a surface grinder, I'll try and get over here. On a surface grinder, remember the part sits on a magnetic table. Brass and bronze and aluminum are non-magnetic. So it doesn't mean that we can't cut those materials, we just can't mount them to the magnetic table, right? So we can mount work holding just like we do on a mill, right? We can put a little toolmaker's vise on there, we can put a 3-jaw chuck on there, anything that is magnetic and that can clamp on the workpiece that we need to cut. Okay, I'll share this screen. Let's just share this for a second. Okay. We understand there's two types of abrasives, aluminum oxide, silicon carbide. All right, two main ones, okay? Those are the two key ones. Those are the ones you need to worry about. We need to understand the makeup of the wheel now. Okay, so a grinding wheel is made up of an abrasive grain, which we have already talked about, right? The abrasive grain is this piece right here. There are tens of thousands, depending on the wheel, right? Thousands and thousands and thousands of these tiny little abrasives. These abrasives, they are held together by the bond. So let's just call it glue. It's not glue, okay, but it's the bond, right? So those grains are held together by the bond. Now, one of the things we need to understand is that we can choose a grinding wheel from based off the requirements of a manufacturer. So let's say, for instance, we have a certain type of material that has to have a certain surface finish, and maybe it's a special metal, maybe it has some special alloys added. So the common aluminum oxide 94.5% abrasive is not going to do the trick. We need something, maybe the abrasive is good, but the purity isn't. Or maybe the abrasive and the purity is good, but the grain size needs to be different. Maybe the grain size and the wheels we have are too large. So you can choose an aluminum oxide 94.5% pure wheel with various grain sizes. So we won't go through them all, but in your Technology Machine Tools book, Unit 71, you will see a chart that shows you all the different grain sizes you can choose. Now, the smaller the grain, often the closer the grains are together, right? You won't typically see the bonds still take up as much space between the grains as you would on a larger grain structure. But it's just something that you have to understand about these grinding wheels. So the bond, in fact, then is what holds those abrasive grains together no matter what size the grain is. There are 6 common types of bonds, guys. 6. I'm only going to make you remember 1. Okay, the most common is the vitrified bond. That's what you're going to find in almost all of the grinding wheels that you're going to have access to in the shop. Okay, but there's the vitrified bond, there's the resinoid bond, rubber, shellac, silicate, and metal. All of those are listed in your Technology Machine Tools book, and they're all described in detail. The only one that you need to worry about is the vitrified bond, because that's the one that you will be using, or that's the one that, I shouldn't say you'll be using, that's the one that your wheels will be using wheels that you'll be cutting with. There's two other things about this wheel that we need to know about, guys. We need to understand grade and structure. Okay, so did you get those four things? Okay, you have the abrasive grain is the first one, the red arrow. The bond is the second one. The grade, which we're going to talk about in a minute. Okay, and the structure. Now, the grade is the degree of strength with which the bond holds the abrasive grains in the bond. Okay, so try and picture that bond, one bond being made out of wood glue and the other one being made out of super glue. Will kind of help you to appreciate more what the grade or the degree of strength that bond holds the grain. Okay, that's what the grade is. All right. Now, don't go tell your instructor that I said that the grade is made out of wood glue and super glue. But I'm just trying to illustrate that you can have there are a range of strength that those grains can be held in that bond. Okay. So if the bond posts are very strong, so that is if they hold that abrasive grain in the wheel during the grinding process, then that wheel is said to have a hard grade. That's a hard wheel, you'll hear machinists say. Okay. Now, if those grains are released rapidly during the cutting process, then the wheel is classified as a soft grade. That's a soft wheel, you'll hear machinists say. So that last part, the structure, okay? The structure of the grinding wheel is the space relationship of the grain and the bonding material to the voids that separate them, okay? The structure of the grinding wheel is the space relationship of the grain and the bonding material to the voids that separate them. So if the spacing of the grains are very close together, if those grains are tightly packed together, then we say that structure is dense, right? It's almost like there's more grains than there is bond. If the space is relatively wide in comparison, then we say that structure is open.